These are the notes for AP Calculus on the topics of implicit differentiation and the second derivative test. So implicit differentiation, remember, is used when you're finding the derivative expressions that are not functions. And also for related rates problems, which we'll review later when we're applying these to real-world problems where things change with respect to time. So this one asks you to find the derivative dy dx, but notice it's not a function that x and y's are all mixed up here. So you start by just taking the derivative of the entire equation with respect to x. And then notice here we've used the product rule on x times sine of y. So we take the derivative of x is 1 times second one sine y as it is, plus first one as it is, x, times the derivative of sine y cosine y. And then remember, key is whenever you take the derivative of a term that doesn't match up with the x here, you have to multiply by the derivative dy dx in this case. X we didn't have to do that because it would just be dx dx, so multiply that by dy dx. Equals, now let's take a look at the other side, the derivative of 3y is 3. Again, we took the derivative of y term, so we have to multiply by dy dx. And then here we've just got to use the chain rule, because we've got 2x inside cosine. So to start on the outside, the derivative of cosine is negative sine. Remember, it starts with a c. Negative sine inside of 2x stays the same. And then times the derivative inside is 2. And that was an x term, so we don't need dy dx. Then, since there's oftentimes more than one dy dx term, in order to isolate it, you have to get them on the same side. So I'm going to leave this x cosine y on the left side, along with the dy dx. And subtract over the 3 dy dx. You get all the dy dx terms on the left. And then I'm going to leave this, put the 2 out in front with a negative, so I'll leave this negative 2 sine of 2x over here. And then subtract the sine y over here. The term without dy. And then what that allows you to do is factor out the dy dx and the GCF out of these two terms. And then you're left with x cosine y minus 3. Leave it alone for now. And then finally you can divide by the x cosine of y minus 3. We'll reduce it out here, so we'll get dy dx. Our derivative is negative 2 sine of 2x. Just leave that sine y there. Divided by x cosine y. So you can see nothing reduces here, so that is your answer for the derivative of dy dx. And remember, on these, oftentimes the derivative has both x and y. These are not functions. So the derivative often will start with both the x and the y coordinate. Well, let's take a look at another one here. And if we take the derivative of this whole equation here, derivative of 4x squared is 8x. And then we take the derivative of x times natural log of y. Again, that's another product rule, where it's x times natural log of y. So we take the derivative of x is 1. It's 1 times the natural log of y as it is, plus x as it is, times the derivative natural log of y is 1 over y. And that's where, since it's a y term, we have to multiply by dy dx. And then the derivative of e to the 2y, that requires the chain rule. We have the 2y in there. So the derivative of e, remember that part stays the same. That'd be e to the 2y times the derivative of 2y is 2, but that's a y term, so we need dy dx. And then, sorry, I ran out of room there. And that's derivative of 4, so e to the 0. Derivative constant by itself. And then, in this case, all the dy dx terms are already on the left. So I'm going to do two things at once here. I'm going to subtract the 8x and the natural log of y on to the right side. And then just factor out the dy dx of the remaining two terms. So you're left with this just becomes x over y. And then plus, you can bring the 2 out in front, e to the 2y. And you can divide by that, x over y plus 2 e to the 2y. So our derivative dy dx will be negative 8x minus natural log of y divided by x over y 2 e to the 2y. So that's our derivative. However, if this was multiple choice, they usually wouldn't leave this little fraction here, x over y, inside the big fraction for the final answer. So you can wipe out the little fraction, simplify a little further by just multiplying the numerator and denominator both by y. We'll wipe it out. So when you do that, we get our derivative, dy dx. That'd be negative 8xy and then minus y natural log of y. Notice this y doesn't get multiplied by this one because that's inside the natural log, this one's not, so it goes out in front. And then divided by, here the y's reduce out, so you're just left with x, and then plus 2y e to the 2y. So that'd be your simplified answer. All right, let's take a look at the next one. Here, this one's asking us to find the second derivative. That's what this notation means here. In terms of x and y, so it has to just have x and y as the only variables in it. So, again, start out with the derivative. Before we can find the second derivative, we need the first derivative. The derivative of 2x to the fifth is 10x to the fourth. And then for xy, again, that requires the particle. So the derivative of x is 1 times the second one y as it is, plus the first one x as it is, times the derivative of y is 1, but that's where we need dy dx. And the derivative of 5 by itself is 0. So then, to solve for dy dx, here there's only one dy dx, so we can just isolate first by subtracting the y over. And y, x, dy dx, and just divided by. So I'm just going to flip the sides here, so dy dx on this side. First derivative, with x and minus y divided by x. And once you have the first derivative, then you can move on to find the second derivative. Find the derivative of this expression with respect to x. And notice here you need to use the quotient rule. Using the quotient rule, well, the derivative of the first derivative would give you the second derivative. And the quotient rule is similar to the problem with the derivative of the numerator. So the derivative of 10x to the fourth is 40x minus derivative of y is 1, but that's a y term, so that's where I need to do y dx. And remember, that whole thing is in parentheses. That whole thing gets multiplied by the denominator as it is, x. And then minus the numerator as it is, and fourth minus y, times the denominator is 1, all divided by the denominator squared. That's our second derivative. However, it's not yet in terms of x and y because we still have this dy dx here. But remember, what we can do to get rid of it is just substitute in, because we already know, remember, this is our first derivative. We already know that's dy dx, so you can just substitute that in right there for dy dx. So let's do that and then see if we can simplify it. So we have 40 cubed minus, now let's substitute in. So our dy dx was 10 to the fourth minus y x, and was times x here. And then to get rid of these parentheses, you can distribute out the negative. So that would be negative 10x to the fourth and positive y divided by x squared. And then you can just simplify it a little further by distributing this x times both of these. So our second derivative. Well, x times 40x cubed is 40x to the fourth. And then here the x is reduced out, so you have this negative right here. Be careful. That negative, since the x is reduced out, the negative applies to the whole thing. The whole 10x to the fourth times y in parentheses. And then we still have negative x to the fourth plus y divided by x squared. And then notice you can distribute out this negative and then combine like terms. So let's see what we get when we 40x to the fourth. This is going to become a negative 10x to the fourth, and another negative 10x to the fourth, combined to be 20x to the fourth. And then this negative changes this to positive y plus another y gives you plus 2y, and then divided by x squared. So there's our simplified second derivative in terms of x squared. All right, let's take a look at another one now. This one says, consider the given curve right here. And first we're asked to find all points, if any, at which the graph of the equation has a horizontal tangent line. So a horizontal tangent line, that means their derivative is equal to 0. So, and then write an equation for each horizontal tangent line. Okay, so let's take the derivative first. This whole equation. And so we've got x squared times y. There's another product rule one. So the derivative of x squared is 2x times the second one, y as it is, plus first one as it is, x squared, and then the derivative of y is 1, but then that's a y term, so that's where you need dy dx. And then on this one, another product rule. This time though, since there's a negative there, I'm going to treat this negative, so you don't need an extra parentheses there, as part of the first term. So negative x times y. And using the product rule again. So the derivative of negative x is negative 1 times y squared as it is. And then normally be plus, but because the first term is negative, we don't see that plus sign, so we just see a negative x. And the derivative of y squared is 2y. And then that's again where we need x. Equal the derivative of 2 by itself is 0. Now the dy dx is already on the same side, so we just have to move the terms that don't have dy dx to the other side. So I'm going to add this y squared over, positive y squared, and subtract the 2xy over. And then factor dy dx out of the remaining terms. So we're left with x squared minus 2xy. And then dividing by x squared minus 2xy on both sides equals our first derivative. Equal to y squared minus 2xy divided by squared. And this one we want a horizontal tangent line. Then we set to make this slope 0 to 0. That makes the numerator has to be 0. So to solve that, notice you can factor out the GCF of y. And you're left with y minus 2x equals 0. And set each of those equal to 0 gives you two possibilities. Either y equals 0 or y equals 0. But again, on these, since we want the points, and these have to be actually on this curve, you take these one at a time and substitute them back in the original equation. So let's start with y equals 0. Put it back in here. Well, if we substitute in 0 for y, let's see what we get. We get x squared times 0 minus x times 0 squared. But the 0 wipes out the whole left side. We get 0 equals 2, but we know 0 does not equal 2, so that doesn't work. So that tells us y can never equal 0, so that's not a possibility. But we do have another possibility that might work, y equals 2x. So let's try the same thing with that. We'll take that y equals 2x, and again, substitute it back in the original equation. So wherever there's a y, we'll replace it with 2x and see if that has a solution. So we'll have, again, if this y equals 0 was our only possibility and it didn't work, then we know there's no horizontal tangent line. That's why it's a safe answer. Sometimes you don't have it. Well, let's see if the y equals 2x works. So we'll have x squared times 2x minus x times 2x squared equals. All right, let's simplify that. 2x times x squared is 2x cubed. If you square the 2x, you get 4x squared times negative x is negative 4x cubed. You can combine your like terms and get negative 2x cubed equals 2. Divide by negative 2 gives you x cubed equals negative 1. And then take the cube root of both sides. And we get x equals negative 1. So this does have a solution when x is negative 1. And then to find y, don't go back to the original equation again. Sometimes that can give you extra points. We already did that, remember? But now, since we know x has to equal 1, you just put it right in here. And then y would have to equal 2 times negative 1. So y equals negative 1. So our point is x is negative 1, y is negative 2. That's the one point where we have a horizontal tangent line. And the equation of the horizontal tangent line, the horizontal lines are y equals, and we already have it, y equals -2. We wrote it down right here when we were finding the y point. Right, that's for part A, and we've done a lot of the work now that can help us with part B. So let's find all the points of interest at which the graph of the equation has a vertical tangent line. So with a vertical tangent line, vertical lines, remember, have a slope that's undefined. Okay. So we can take a lot of the work we've already done from part A to help us out here. All right. First thing we can do is to make the derivative, which we already have here undefined, we would just take this x denominator, x squared minus 2xy, and set that equal to 0. And then factor out the x, leave you with x minus 2y, 0. So again, we get a couple possibilities, either x can equal 0 or x equals 2y. So again, to figure these out, we need both coordinates, so take the x equals 0 and substitute in the original equation. And let's see what we get. Well, when we do that, we get 0 squared times y minus 0 times y squared equals 2. Again, 0 wipes out this whole left side of the equation. We get 0 equals 2, which doesn't work. So that tells us x can never equal 0. And then try x equals 2y. Substitute that in the original one. So we get 2y squared times y minus x times, oops, sorry, I forgot to put 2y there. 2y times y squared, sorry, I ran it there, equals 2. Now let's simplify that and try to solve it. So that'll give us 4y squared when you square 2y times y is 4y cubed minus 2y times y squared is 2y cubed equals 2. Then just combine your like terms. 4y cubed minus 2y cubed is 2y cubed. Divide by 2, y cubed equals 1. And take the cube root of both sides. So y is equal to 1. So we get y equals 1. And then to find x again, go back to the original equation again. You might get additional points that don't actually work. Just go right back here. So x then would equal 2 times 1. So x equals 2. So our point where we have a vertical tangent line, there's just one in this case. Sometimes you have more than one, sometimes you have none. Here we've got x is 2 and y is 1. And the equation of that vertical tangent line, right in the equation of each one, would be x equals 2, which we already wrote down here. All right, let's take a look at the next problem here. This one we're given, considering this curve and the x coordinate, find all the points on the curve with an x coordinate of 3. So if we're given the x coordinate 3, to find the y coordinate, you just, like you know, let's substitute in here to solve for y. So we'll substitute in 3 for the x's, so it'll be 3 squared minus 3y, y squared minus 1. And that simplifies to be 9 minus 3y squared minus 1. And then since the y squared is already positive on the right side, I'm going to make the left side equal to 0. Get y squared plus 3y. Add the 3y over and subtract the 9 from -1, gives you -10. And then factor that. Actually, -10 that adds to be 3 would be -10, 2, and +5. So we get y equals 2 or y equals 2. So the points, those correspond to, since x is 3 for both of those, would be 3, 2, and 3. So that answers part A. And then it says write the equations of the lines tangent to the curve at the points found in part A. So we need two different tangent points for each these points. Remember, to get the tangent lines, we need a point of tangency, which these already are, and the slope, and that's where we need the derivative. So let's go ahead and find the derivative of our equation here. Go. So we're taking the derivative of this whole equation here. The derivative of x squared gives you 2x. And then for negative x and y, use the product rule, negative x times y. The derivative of negative x is negative 1 times y as it is, plus negative x as it is, so you don't see that plus sign. The derivative of y is 1, but that's where you use dy dx. Equal the derivative of y squared is 2y. And then again, we need a dy dx. And then this time it's probably easier if you get the dy dx is on the right because you only have to move one term. So I'm going to leave this 2x minus y on this side. Leave this 2y dy dx on this right side. And just add over the x dy dx. Right side. That way we can factor out the dy dx here. On the side, just leave the left side, 2x minus y. And then we're left with 2y x. And then divide by that. So I'm just going to switch the sides. So our derivative dy dx is 2y plus x divided by 2x minus 1. Oops, go back around, sorry. 2x minus y divided by 2y plus x. There we go. All right, now let's go ahead and find our slope at each of these points. You can start with either one first. So let's say we start with 3, 2. Remember the way you write that? Put a vertical line when x equals 3, 2. So you have 2 times x is 3, y is 2, or 2 times y is 2, plus x is 3. Gives you 6 minus 2 is 4. 4 plus 3 is 7, so that's your slope. So you can write this tangent line as y minus the y coordinate 2 equals 4/7 slope times x minus x squared. All right, let's find the slope at the other now. So dy dx, specifically when x equals 3, again, and y equals negative 5. So that would be 2 times x is 3 minus y is negative 5 divided by 2 times y is negative 5 plus x is 3 gives you 6 plus 5, so 11 over 2 times negative 5, negative 10 plus 3, negative 7. So we get negative 11/7 is our slope. So tangent line, I'll just write over here so you can see a little better, would be y minus negative 5, so y plus 5 equals negative 11/7 is our slope, times x minus 3. let's take a look at the next one here. So this one says find all the points x, y on the curve where the line has tangent to the curve has a slope of 4/7. So dy dx. We have the same curve as we had on the last part. So this is part C to this one. Notice 4/7 should sound familiar because we got that at the point 3, 2. So we know 3, 2 should be one of our answers, but we don't know if that's the only point that works. It might be, it might not be. So let's make sure that's the only one, or find any others if there are any. So here's our derivative right here. Dy dx is 2x minus y divided by 2y plus x. We'll start with that. So 2x minus y over 2y plus x. That's what it has to equal. And then if you cross multiply here, all that, you get 7 times 2x minus y gives you 4 times 2y plus x, 8y. We can subtract the 4x's from both sides. Add the 7y to both sides. You get 10x, 17y. And if you solve for the x, divide by 10, and you get x equals 3y over 2. Or you could solve for the y here, and get y equals 2x over 3. Either way is fine. And then we're going to take that, and since it has to be a point on the curve, substitute that in for all the x's in this equation to try to solve for what y would have to be. So for all the x's, we're going to substitute in 3y over 2. Instead of this x, 3y over 2 squared, x, oops, sorry, plug in the 3y over 2, right? 3y over 2 for that x times y. So let's simplify and see if we can solve for y. So if you square out the 3y over 2, you get 9y squared over 4 minus 3y squared over 2 y squared. Then if you want to make it a little easier to solve, you can wipe out the fractions. The least common number will be 4. So if you multiply the whole equation by 4, we'll get 9y squared minus 4 times 3 is 12, divided by 2 is 6. 6y squared, y squared minus 1. Combine your like terms here. 9y squared minus 6y squared is 3y squared. Y squared, whoops, I accidentally forgot to distribute the 4 times the negative 1, so it should be y squared minus 4. And I forgot to distribute times the y squared also, sorry about that. 4y squared minus 4. We get 3y squared equals 4y squared minus 4. Then subtract over the 4y squared gives you negative y squared equals negative 4. Divide both sides by negative 1 gives you y squared equals 4. Take the square root of both sides. Get y equals plus or minus 2. Let's take an even root of both sides, so you need the plus or minus. So we can substitute those in one at a time for y right here. So if we plug in positive 2, we get 3 times 2 divided by 2 is 3. So positive 3 for x goes with positive 2 for y, so 32. And if we substitute in negative 2, we get negative 6 over 2 is negative 3. So negative 3 for x goes with negative 2. So we did get the point we expected, remember, from the previous part. 3, 2, we know, gave us a slope of 4/7. However, that wasn't the only one. Negative 3, negative 2 also worked in this case. All right, now let's go ahead and take a look at the second derivative test, which oftentimes is on these implicit differentiation problems. So let's first review the first derivative test, which is the most common way we use usually to find our local mins and maxes. Remember the first derivative test? You draw your number line, and for the first derivative x, have some critical numbers. Let's say 0 here and 0 here, and you find that it's positive and negative, positive. Then when the first derivative changes from positive to negative right here, that'd be a relative max. And the first derivative changes from negative to positive, decreasing and increasing, that'd be a relative minimum. And that's how you can determine your local minimums and local maximums. Okay. That's the first derivative test. But sometimes you don't have enough information to get a complete number line like this to figure out where your relative mins and maxes are. And oftentimes it happens on these implicit differentiation problems that we've been going over. So let's see why this one works here. So the second derivative test says if you know the first derivative equals 0, well, that's the slope 0. You have a horizontal tangent line. And the second derivative is greater than 0 at some point c, that means it's concave up, shaped like a cup. Let's draw what that would look like. Okay. Well, we know it's concave up, shaped like a cup, and the slope is 0. It'd have to be like right there at c. And you can see that's a relative minimum, or local minimum at x equals 0. Okay, one way to tell it if you're just looking at that one specific point. And also, it also works if the slope is 0 at that point c, and this time the second derivative is less than 0. That means it's concave down, shaped like a frown. So if we draw that, concave down, shaped like a frown, and the slope is 0 right there, let's see. You can see that would be a relative maximum, or also called a local maximum. So it's an alternate way of figuring out our local mins and maxes. Again, oftentimes used when sometimes you can use it instead of the first derivative test, even though you could have used the first derivative test, but oftentimes we use it when we can't use the first derivative test. There's just not information to use. Okay, so let's take a look at this next example here. Okay, so it says that y equals f of x be a function that contains a point 0, 2 and has a slope derivative given by this. To determine whether this point is a local maximum or local minimum and justify our answer of f of x. All right, so for the second derivative test, we first need to see if it makes the first derivative 0. Otherwise, we can't use it at all. So let's go ahead and substitute in this point 0, 2 for x and y. See what we get. So if we substitute in 0 for x, we'll have 0 times y, 3 times 0, oops, sorry, 2 for y. 0 times 2 for y, 3 times 2 for x. See, that does give you 0. So that means it could be, it's a critical number, critical point, and that could be a relative min or max potential. If you don't get 0 here, then it can't be a local min or max. You can stop right there. But since it is 0, we could have one. And now we just need to find the second derivative to determine the concavity. So take the derivative. The first derivative is the second derivative. E squared y squared equals, on x times y, we have to use the product rule. Take the derivative x is 1 times y as it is, plus, first one as it is, x, oops, sorry, I did x, but I didn't write down, x times the derivative of y is dy dx, times dy dx, derivative y term, and the derivative of negative 3x is just, and then substitute in our 0.02 into the second derivative. And again, what we're looking for is to see whether it's positive or negative. Well, 0, y. If it's neither, then we won't be able to tell if it's a min or a max. usually it's positive or negative. That can tell us. So y is 2, plus x is 0. And normally you'd have to plug in the whole expression for dy dx right here in for dy dx. Here we don't need to do that because we already know at this point, we already figured out it makes the first derivative 0. So I plugged in the first derivative, already know it's going to be 0 from right there. And then minus 3. So the 0 wipes us out. We just end up with 2 minus 3, which is negative 1. And since it's negative, that tells us concave down, shaped like a crown. We know the slope was 0 and it's concave down. So you can see that causes it to be a relative or local maximum. All right, and now all we have to do is state that and justify your answer. So we can say 0, 2 is a local maximum. And to justify, there's two things we have to say. We have to say since the first derivative, dy dx, specifically when x equals 0, y equals 2 equals 0, it has to make the first derivative 0. And the second derivative, d squared y dx squared, at x equals 0, y equals 2, is how you justify it with the second derivative test. As opposed to, remember, the first derivative test justification for a local max would be since f prime of x changes from positive to negative at x equals 0. In this case, you can see because we only have this one point on the function, there's no other points we really know on the function. So if you try to draw your number line for the first derivative test, you just don't have enough information. Because we don't know any other points to test into the first derivative. We only know this one point, the original function. All right, let's take a look at the next one now. Okay, so this one kind of combines what we were going over earlier with implicit differentiation with our secondary test also. Part A just says find all the points where, it should say the curve, or this one, where the curve has a horizontal tangent line. The horizontal tangent lines are where the derivative is 0. All right, so the derivative is 0 here. We need to find the derivative first. So the derivative of x squared is 2x plus 4y squared is 8y, and then the derivative of the y term, and that's where dy dx. The derivative of 12 is 0. And then to take the derivative of 2x y, we have to use the product rule. So we take the derivative of 2x is 2 times y as it is, plus 2x as it is, times the derivative of y is 1, but that's dy dx. And then there's more than one dy dx, so let's get them on the same side. So I'm going to leave this 8y dy dx over here. And then subtract over the 2x dy dx. Leave this 2y over here. And subtract the 2x. I factor out the dy dx. And you're left with 8y minus 2x. And then divide by 8y minus 2x. And notice on this one, you can actually reduce it if you want to. You don't have to, but everything's divisible by 2. So you could reduce it and just get y minus x divided by 4y minus x. Okay. And then remember, for horizontal tangent lines, where the slope is 0, you set the numerator equal to 0. And when you solve that, you get y equals x, x equals y, either way. And again, on these, you have to find the other point. You have to substitute back in the original equation. There has to be a point on this curve. So you can substitute y for x or x for y. I'm just going to replace all the y's with x. Either way, we end up giving you the same answer here. So we'll have x squared, or substituting x for the y, x squared equals 2x. So we get 4x squared plus x squared. Those are like terms. Gives 5x squared. 12 plus 2x times x is 2x squared. Then you can subtract the 2x squared over. You get 5x squared minus 2x squared is 3x squared equals 12. Divide by 3 is x squared 4. Take the square to both sides, and you get x equals plus or minus 2. Give root to both sides, so you need plus or minus. And then you can substitute those in one at a time here. If x equals 2, y is the same, y equals 2, so one of our points is 2, 2. And if x is negative 2, y is negative 2, so the other point would be negative 2, negative. In this case, there's 2 points where we have a horizontal tangent. That's part A, and then part B says that each of these points determine whether the curve has a local minimum or a local maximum. So again, on this one, this would be tough to use the first derivative test. We do have the original function here, so we could try to find some more points on here and test on the number line, but that's going to be a lot more tedious than just using the second derivative test. Since we already know there are these points, and they already make the first derivative 0, we just have to find a second derivative and determine the concavity case. So we're just going to take the derivative of our first derivative here using the quotient rule. The derivative of the first derivative is the second derivative. And then you take the derivative of y is dy dx. Minus derivative of 1. Put that times the derivative of the numerator times the denominator as it is. 4y minus the numerator as it is, y minus x. Times the derivative of 4y is 4, and that's a y term, so we need dy dx. Minus the derivative of x is 2. All divided by the denominator squared. And normally, if you had to get this in terms of x and y, we'd have to substitute the first derivative of y dx. But remember, we don't have to do that here because all we're concerned with is that these 2 points, do they make the first derivative, sorry, do they make the second derivative either positive or negative? So we can actually just substitute in right away. All right, so let's substitute in the point 2, 2. Now, the key is, remember, one of the reasons why we don't have to substitute in, dy dx, we already know this point makes the first derivative 0, so that'd just be 0 minus 1. And then we can substitute in here 4 times y, which is 2, minus x, which is 2, minus y is 2, x is 2, 4 times dy dx, we already know makes 0, minus 1, all divided by there's the square here, we don't have to really worry about that. So notice this 2 minus 2 is 0. That's going to wipe out this entire second term here. 0 wipes this whole thing out. That's fine. And now we just have a negative here. Negative 1 times this a minus 2 is positive. So it's just a negative times a positive divided by negative. So divided by positive. Negative times a positive is negative. That means it's concave down, shaped like a frown, which means we have a relative or local maximum. And now we know that the point 2, 2. This one we didn't have to justify. If we did, we justify it just like that other one we did. Is the local maximum. And then let's just substitute another point. And specifically when x is negative 2 and y is negative 2. And again, this point, just like 2, 2, makes the first derivative 0. be 0, minus 1. This time we're going to substitute in negative 2 for y, and negative 2 for x makes this positive 2, minus negative 2 minus negative 2 makes it plus 2 again. And again, it makes the first root of 0. 4 times 0 minus 1. All divided by the denominator is always squared, so that's always positive. Don't have to worry about that. Again, notice something similar happens with this point. Negative 2 plus 2 is 0. That wipes out this entire term over here. And then this time, though, we have a negative 1. And this is negative 8 plus 2 times another negative. Negative times a negative is positive. That means it's concave up, shaped like a cup, which means it's a relative minimum. So we can say negative 2 is a local minimum. And that concludes the notes for AP Calculus on the topics of implicit differentiation and the second derivative test.